as promised, we have a little bit left on interactions to do, and then I will let you have your own time to work on homework 1. So we have, let me see here. We were inside example 2C, looking at different ways of coding categorical variables. So there's one interaction that I'm interested in these example data. It was the interaction between a binary variable for gender and a 3-category variable for dementia group. You can decide to make one of those variables continuous, both of them continuous, or neither. And so we had done the first model, which is in which I did the coding myself so that they're being treated as continuous. So that was where we have dem NF and dem C as the contrast for each of the none versus the alternative groups. And accordingly, everywhere in the code where we're asking for simple effects, all you need to put is 0, -1, or 1 to turn them on or off. So we did that part. Are there any questions on that setup? Okay. Then I switched dementia group to be categorical in the syntax, which changes how you ask for things. So in SAS, it is putting dem group on the class statement. So it understands how many contrasts you need to differentiate however many groups are in your data set. The analog in Stata is the I.dot command instead of C.dot. Because there are 3 dementia groups, everywhere in the code that you see dem group, there's 3 values that you have to mention, what you want to happen for each group. So for instance, if I want the group difference between the first 2 groups, I need a -1 and a 1, and the third group is irrelevant. If I want the difference between the first group and the third group, that would be a -1, the second group is irrelevant, and a 1. And that pattern would be echoed across whatever interacting variable such as gender here. So this is what the setup would look like if you have an interaction between a continuous variable and a categorical variable. You are allowed to use LS means or margins to be able to get group differences at any point along the continuous variable that you want. So I'm explicitly holding these things equal to averaging across gender or each specific gender to get the relevant simple effects. And I think that was about where we left off. Okay. Are you ready? Yeah. Thank you for your continued enthusiasm. I know. Well, see, there's a reason. I told you last time that I prefer to do it this way. I prefer to only have one variable at a time be categorical if I can help it at all. So for instance, if it's interacting with a binary variable, that's easy to treat it as continuous and have the 0 versus 1. But if you have 2 categorical variables to interact, asking for the relevant comparisons and interaction contrasts gets a little more challenging. So let me show you what that is going to look like. So in this case, I'm on page 6 in handout 2C. I've added gender to the class line. So now it's going to make my contrasts for me. This gender variable is coded such that men are the 0 and women are the 1. Remember what the rule is when you put a predictor on the class statement? Who becomes the reference? The higher. So the 1 is the new 0. So for instance, skipping ahead to some output here, women are the 1 are my new reference group. So it takes your dummy code and essentially makes it backwards. And that's where my head blows up. And for that reason, on your first homework, I suggested using opponent type, treating it as continuous to avoid this type of confusion. But that's not all. Note the series of digits that has to follow the interaction of gender by dem group everywhere. There's 6 of them. Why 6? 2 times 3. So every time you ask for some sort of comparison, you have to say what happens to every possible cell, every possible combination of the categorical variables. Now 6 isn't too unwieldy, but what if you had 2 4-category variables that are interacting? How many numbers do you have to type every single time? 16. That's where it gets tricky. So in order to get simple effects, you have to pay attention, very close attention, as to how you know what the order of the numbers are. I learned the hard way that it is dictated by the order of the variables on the class statement. In this case, it goes all the way through one level of the first variable before starting on the second. So I have this, it's men none, men future, men current, then women none, women future, women current. How did I ever learn that? How would I figure that out if I don't know? Let me show you a trick that I found. I don't know if Stata has this capability because I couldn't find it, but I wanted to show you how to do it in SAS. So this is the file that goes with this example where I gave you the original SAS code. I'm going to run this model that we're on right now, adding in an option on the estimate statement that's a slash and an E. And I'll show you what the output looks like after doing so. Let me turn the HTML on real quick because that'll be prettier to look at. Ready to There we go. So here's my output, my solution for fixed effects, which we'll go over in just a second, the omnibus test of the main effects and interactions of categorical variables, and then this special box right here, coefficients. This is your trail of breadcrumbs. It tells you the order in which your groups go. And it also tells you what you told it. So for instance, this first line right here, what I asked for is the gender difference for the none group. So the main effect of dementia group is irrelevant. The gender difference is the contrast of men versus women. And I then want to find out the gender difference for the none group requires figuring out which of these values refers to the none group. So it's -1 where the men none group is, skipping over the rest of the men groups, and then 1 where the women none group is, skipping over the rest of those. So I know that I have it right because of this table. It shows me that I have filled in -1 and 1 for men versus women. I filled in nothing for dementia group, and then I've put a -1 for men none and a 1 for women none. So this is your trail of breadcrumbs to figure out which things they go on. Also note, these things are missing, which means I'm implicitly asking for all of this stuff holding this stuff to 0. And the intercept isn't relevant anyway, but the other covariates would be if they were part of an interaction. So then the other two have the same format, just shifting over one cell where the -1 and 1 is to get the gender difference between group 2 and then the gender difference between group 3. Yeah?
Can you explain again why the demographic group there is all 0?
Because what I'm asking for at this point, let me make this a little bit bigger. There we go. So we're on this part right here. What I'm asking for is the gender difference. So the only terms that go into this statement are things that have gender in them. Dementia group by itself doesn't have gender. So I'm including that just to keep, so you can see the pattern,
Oh, I see.
right? So when I ask for the dementia group differences, the main effect of gender is irrelevant. So does that make sense? Okay. So then in the next set, let me get these two. Now I'm asking for the simple effects of group conditional for each gender. That means I need to start with the effects of group. So this is group 1 versus group 2. I have to figure out where that falls. So this is, the first 3 values are for men. So I'm asking for the group 1 versus 2 for men and ignoring the women. The opposite in the next sentence, ignoring the men, asking for it for the women. So once you know which is which, it becomes straightforward to fill this out. So here's group 1 versus group 3 for men, for women. And then group 2 versus group 3 for men, for women. Okay, how are we doing? That was a laugh? No. A little overwhelming, right? A little bit. But there's a pattern to it. So let's look at that part of the output so far. By the way, the Stata code to do that same thing is another new special symbol in Stata, the @ sign. Have you seen this before, Stata people? Oh, hooray, I get to teach you something. So, hashtag is how you tell it about interaction term to begin with. Within margins, there's an option involving the @ sign, where the first variable is what you're asking for comparisons across per the variable after the @ sign. There's an analog in SAS called slice, actually, that does the same thing, and it's holding these covariates equal to whatever you say and using the degrees of freedom that are based in the model at this point. So I'm asking for, in the first line here, the simple effects, differences between men and women for each dementia group, and then asking for the differences between groups for each gender. So those 2 lines together give me all possible combinations. Now, why do I need to ask that? Because what's given by default is only some of that. So at this point, the default output, the solution for fixed effects, is not terribly useful because it is only giving some of the possible comparisons, the ones involving the reference group. So gender, the reference group is now women. That means that the intercept here is for women. The reference group for dementia group is current. So this new "you are here" sign for our model is women with current dementia. If I go into the effects of dementia group right here, those are specifically for women, my new reference point for the model. And so I know that the future group in women is higher than the current group by 13. The none group in women is higher than the current group by 19. Let's do that one. And that one. So 19 is the difference between the none and current group in women. What happens to that difference in men? Yeah, less positive, so it's smaller. The difference is smaller in men. Same pattern for the 13. 13 is the difference between future and current in women. It is smaller by 8 in men. What we don't know yet is the difference between none and future in women versus men and whether that's different. So we're missing some of the information. Then we get to this box down here, Type 3 tests of fixed effects. So the ones for age, grip, and age by grip are exactly the same as what's up above. It's just a repeat of the same information. The rest of these are different. So let's look at the main effect of gender up here. In the solution for fixed effects, the main effect of gender has a t-value of 3.7. Down here, the main effect of gender has an f value, which should be t squared of 19. 3.7 squared is not 19. P-value of 0.002 is not p-value of less than 0.001. So we talked about this briefly. Do you remember why these are different?
Average across or sample.
Yeah, one of them is at 0. Which one is at 0? The top one. And what does 0 mean currently?
Average across the groups.
Not in this top table. Top table, it's holding it at the reference group, which is now current. So this is the gender difference in the current group. This is the gender difference in what group? Down here. Averaged across the groups. This next line that I've highlighted here, this is the omnibus main effect of dementia. Whether or not there's a main effect across the three groups, that is now marginalized across gender. So it's the group differences on average. And we know that somehow they're significant, but we don't necessarily know exactly which groups are different from each other. Likewise, we know that we have an interaction term between gender and dementia. We know that it's significant, but we don't know why. So that's why I'm making you ask for this stuff. Because at this point, these results right here that show up by default are essentially useless. Why is that? That's a strong statement, right? It's useless. Because what those results refer to, the main effect of gender is this difference right here in the margins. The main effect of dementia is this difference out here in the margins. And the interaction term, which gives us 2 degrees of freedom and a significant F, is saying there's something going on in the middle. What's going on? We got to figure out which of these differences is different from the other. And there's 3 possibilities. It could be that the gender difference in none is different than the gender difference in future. The gender difference in none is different than the gender difference in current. Or the gender difference in future is different than the gender difference in current. One or more of those may be true, but we don't know. So that's where the interaction contrasts come in, and those are built from the simple effects. So what I've gone over thus far is how to get simple effects within these cells. Gender difference for each dementia group, each pairwise difference within genders. What we want to know next then is which of these differences differ. Okay, are you with me? Maybe? So when I first saw this, I lost my mind. I was like, how in the hell am I ever supposed to figure this out? But once I finally got it, it was like magic. This crazy pattern of 1s and 0s. This comes from literally subtracting the lines above it. Let's do the first one. sex difference for none versus sex difference for future. An interaction term means that the difference is different. That's this. So if I take line 2 up here, sex different for future, and I subtract line 1, we end up with the main effect of gender dropping. We end up with the main effect of dementia group dropping. And then this crazy pattern of -1s and positive ones comes from here. So -1, 0, 1, 0, -1, 1. Then we go over here. 1, -0, 1, 0, -1, -1. So it's taking the cell-wise comparisons for one group and flipping it for the other, flipping the direction. So it's essentially adding the cells together on the off diagonals to do this. Same idea for the next set and the next set. So if we put it all together, then we get the simple effects and the simple effect differences. So what we just did in terms of the contrast is this. The gender difference for none is different than the gender difference for future by this much. This much is not significant. So we've knocked out one possible reason for this 2 degree of freedom interaction. It's not that the gender difference between none and future is different. How about these two? Is -2 different from -10? Survey says yeah, they're different by 8. So that's one possible explanation for the interaction term. How about this -2 and this minus? That's the 7 right here. So the onus is on you if you have multiple grouping variables and testing interactions to figure out exactly where the differences are. Otherwise, just saying there's an interaction and describing the simple effects is insufficient. One of the things that I see people do in practice when I'm reviewing papers, for instance, would be to give up and start doing t-tests. Have you seen this? I have a significant interaction of a 4x4 interaction. I'm just going to start using separate t-tests to compare all the cells. Split the data up into groups and do subset analyses. Cool or not cool? What do you think? I'll give you a hint. There's a reason I didn't show that to you. The answer? Not cool. So now I'm reviewer 3. I have a problem with the follow-up analyses conducted in which the analysts ran separate t-tests for every possible group. What's the difference? Why would these results differ from that approach? Sample sizes, it understands how many people are in each group. So this allows for different sample sizes. But what are we assuming about all of these groups with respect to their variability? It's the same. Yeah. That's the homogeneity of variance thing that comes along with regression. Now, they don't have to be the same. We could test whether or not the variances need to differ by group, but that's not done yet. But if you run a separate t-test for every single one of these possible comparisons, the error term of that t-test is based on only those two groups. So it's entirely possible that you would get inconsistent results because these error terms are all based on the pooled error term across all the data, not pieces of it. So you don't want to take your model and break it into pieces to get specific answers. You want to be able to ask for everything you want out of one giant model. And now you can see why I don't prefer this. It's a lot easier for me to think about creating contrast for one of the variables myself so that I cut down on the sheer number of values that I have to keep track of after each combination. So that's my approach. And if you want to have some example write-up for all of these analyses, it's in the back of Chapter 2. So, one other piece of this, I should note that all programs allow you to correct for type 1 error inflation with these estimate statements or these LS mean statements. I don't bother because I don't see these extra tests that I've asked for as any different than the ones that are provided by default. 1 in 20 of these is wrong, and I don't make that distinction. So if someone yells at you and you need to include it, go to the user's manuals for these programs, and you should be able to ask for Bonferroni corrected p-values or Winfeld or whomever they want you to use instead. All right. So questions? Then that is all I wanted to say about that. As promised, I'm giving you the rest of the time to work on your homework 1. Let me know if you're having problems accessing either SAS or Stata, or if you're unclear about what the instructions are. And otherwise, have a good weekend. Thanks for coming.